Now we introduce the concept of ring homomorphisms. Let R and S be rings. Then a function from R to S is a ring homomorphism if it satisfies the following two properties. First, phi of the sum of any two elements from R is sent as the sum of the phi values. So it preserves sums. Second, it preserves products. For any two elements, phi of x times y is equal to phi of x times phi of y. So the function is additive and it's multiplicative. Notice this means that it's also a group homomorphism with respect to the additive group structure. And that's a fact we use an awful lot for some of the proofs. So given a group homomorphism, recall that the kernel are those elements that are sent to the additive identity. And a fact we learned when we studied group homomorphisms is that a group homomorphism is injective if and only if the kernel is the identity element. Well, since this is an additive group homomorphism, that same result is still true for ring homomorphisms with the exact same proof. You're just only focusing on the addition. So here comes our first example of a ring homomorphism. I don't think this one's in the book. We're going to go from the complex numbers to the complex numbers. It's called complex conjugation. Turns out to be a very interesting function, and this is its algebraic property. So here's the proof. You have to check these two properties. Notice if I were doing a full written proof, I would actually need to say let a plus bi and a prime plus bi be complex numbers. And do that twice, and I would need to say first we show phi is additive, then we show phi is multiplicative. So there's another way to write it. But here's the actual key step once you're ignoring the sentences. So how do you add two complex numbers? You add their real part and you add their imaginary part. What does phi do? It negates the imaginary part. But what is phi if the sum of the individual things? Oh, there's a mistake there. That should be a plus. Phi of a plus bi should be a minus bi, and phi of a plus bi, a prime plus b prime I should be a prime minus b prime I. These two terms differ by commuting the middle two elements. So we have equality there. So we do in fact see that this function is additive. More importantly, it is also multiplicative. If you multiply two complex numbers, you get a prime minus b prime is the real part, and b prime plus a prime b is the imaginary part. The function conjugates, so it replaces plus with minus for the imaginary part. It turns out you can actually see that you can factor this as a minus bi times a prime minus b prime I. And the first factor is just the complex conjugate of a plus bi, and the second factor is the complex conjugate of a prime plus b prime I. So complex conjugates preserve products and sums. So it is in fact a ring homomorphism. It also turns out to be an isomorphism, which means the same thing it does for groups, that this is actually a bijection. And that's not too difficult to prove. When is a complex conjugate of a number equal to 0? Well, the imaginary part turns out to be 0 and the real part turns out to be 0. So congratulations, the kernel has to be trivial, it has to be injective. And surjective is not too hard. You get a plus b because this conjugation map is an involution. The conjugate of the conjugate is the original number. So surjectivity is, yeah. What I'm saying there is phi squared is the identity function. So phi is actually its own inverse. So there's another way to prove that it's a bijection. Another example of a ring homomorphism is given by the following. We send the integers to z mod nz by sending an integer k to its congruence class mod n. So here I'm going to use the k bar notation. To represent the congruence classes. We know before that sometimes I drop the bars, it depends on the context, but here I'm going to keep the bars so it's clear which I'm talking about since I have integers in the same slide. We need to check that it's a ring homomorphism. What's phi of k plus L? It's the congruence class of k plus L. By definition of sum, that's also the congruence class of k plus the congruence class of L. But that's just phi of k plus phi of L. Same thing happens with products. So now we look at the kernel of this map. It's those k such that k bar is equal to 0 bar, which means those k that are congruent to 0 mod n. Which integers are congruent to 0 mod n? The ones that are divisible by n, which means you're just looking at n times z. At last, another favorite example. We'll let q of x be the ring of polynomials with rational coefficients. Technically, you can use any ring here, but I want to make it as accessible as possible. Just pick your favorite rational number, then you could define a function from the polynomial ring to q. This is called the evaluation homomorphism. What do? You replace x with a in any polynomial. So in other words, given a polynomial of this form, the coefficients are p sub I. What are you really doing? You're substituting x with a. And since you're working in a ring and multiplication is well defined, for non-negative powers, a to the I is well defined. It's an element of the ring. Pi times a to the I is an element of the ring. This summation is an element of the ring. This actually is a well-defined element. So for a given polynomial, this is actually an element in Q. So this actually is a well-defined function. It is worth noting that this is a little different than the way we're used to thinking of things. You're used to thinking of you fix a polynomial and you vary x. But for this homomorphism, what you're doing is the opposite. We are varying the polynomial for a fixed x value. Because we're evaluating all the polynomials at the same point. And the miraculous thing is that if you do that, the result is actually a ring homomorphism. So let's see why that is. Let's take two polynomials p and q. Let's see what happens if you evaluate their product. Well, remember this is what their product looks like. All I've done is replace x with a now. The a distributes. And not only does the a distribute, I break the a up like so. To a to the k with the p sub k and a to the I minus k with the q's. And why would I want to do such a thing? Well, I could try to rewrite this summation as a double sum. and replace the I minus k with the j. And you can check that this actually does in fact give you the same exact ordered pairs and the same exact number of terms. And if I do that, I will see that what I get is what you get when you FOIL this product. You're taking one term from here and one term from here and multiplying them together, all possible ways you can do that. So this is the expansion of this product of two polynomials. But this is just what happens when you evaluate P at A, and this is what happens when you evaluate Q at A. So we see then that this is actually multiplicative, provided you're willing to buy this sweeping under the rug here, that you actually get all the ordered pairs. Why do you get all the ordered pairs? Well, this is the substitution where you set j equal to I minus k. And then you also have to observe that when k is bigger than I, this term is 0. So you only really need to care about when k is going from 0 up to n as possible options. And then as k is going from 0 to n, j ranges from all these possible values. Of course, we only showed multiplication. Here's addition. Addition's actually easier. If I add the two polynomials, I just add the coefficients point-wise or term-wise. Place x with a, distribute the sum, and then realize I've just evaluated the two polynomials separately and then added the result. So why is this ring homomorphism useful? Well, what is the kernel? It's those polynomials such that when you evaluate at a, you get 0. In other words, those polynomials where a is a root. And we'll come back to this later when we try to find a better way to express that fact. But I'll just say there's a whole branch of mathematics that's really, really hard, involving systems of polynomial equations called algebraic geometry. And there, this type of calculation and these types of ring homomorphisms become a lot more important.